let's start with a quick review of RMS. So the thing is RMS, root mean square, you're kind of, you're trying to make it kind of a DC equivalent, all right? So that if I have a sine wave, right, and I take the amplitude times 0.707, right, I'm going to get a voltage or current, right, that I can use in my power equation. So VRMS squared divided by your resistance would be like VDC divided by the resistance. The RMS of a DC signal is the DC signal itself, right? So it's just a convenient way to keep track of powers. And so if you have a 60 hertz signal and the RMS value is 110 volts, RMS, that's what's coming out of your socket, right? And the understanding is a 60 hertz AC signal, right? Um, the thing about RMS is that that number doesn't tell you the frequency, doesn't tell you how you got there. You can have an RMS of a pulse, right? But once you have a number, now you can just compare it to a DC equivalent, right? But it certainly doesn't tell you how you got there. It strips out all the information. So if I say there's a 110 volt RMS coming out of your wall socket, yeah, that's for a sine wave, right? But in 60 hertz. Um, so you can find the amplitude. You can use LT spice, right? Okay. So, in a way, we've been doing uh, identifying systems from a Bode plot for a while. But what the way we've been doing it is here, do this Bode plot, right? And then check your work. Is it what it is, right? Now I'm identifying systems from a Bode plot when I grade your exam questions, right? And I can tell that it is or it isn't the system in question. But now we're going to look at it, okay? And but the thing is in order to do it, you have to be able to tell by looking at it, do you have a low, high band or notch filter, right? Because that will determine which equation you're going to use to backfit, right? You can put in numbers as much as you want, and if you've got the wrong filter, it's going to be somewhat meaningless. So for a first order low pass, right, the things that are you're looking for, right, is that at low frequencies it's constant and then it rolls off and it rolls off at minus 20 dB per decade. All right. So you would have to, take a decade, all right, and extract, if you go a decade and it goes down by 20 dB, well, then it's first order. The other thing is the phase maxes out at minus 90, where there's a minus 90 phase, because if it's inverting, right, it won't start at 0, but you're really looking for, I was starting at a number and I ended up minus 90 degrees at the higher frequencies. So it's really the change. All right. But here's our transfer function of a low pass first order filter. You have omega naught, and then you have a gain DC. Well, the gain DC in this case is 0. So what's H at 0? Well, it's not 0 dB. You have to convert it to gain DC, right? And it's 1, right? Then what's omega naught? Well, there's an LT spice. It's easy just to take half of the phase difference. In this case, the difference is 90. So half of it is 45, and just read out to the phase line and then down, and it's a kilohertz. Now, in practice, that's very difficult because phase is not really phase, it's delay divided by the frequency at which you're at, or the period. Oh, that's very, thank you. Go to the board. So just as a quick reminder, right? Have a sine wave, right? And then a sine wave that I'm comparing it to, right? You have the period, so you have to measure the period, right? And you have to measure that time delay, for which then you can calculate phase. So you've got to be able to measure the period and the time delay fairly accurately. And so here's my oscilloscope with my probes. I'm not showing ground, right? So I'm measuring, this sine wave here, the output there, right? And just even draw the way I drew the cables, one cable is longer than the other, or maybe it's not calibrated right. So what I have found is that it is very difficult to measure the phase. And also parasitic inductors and capacitors make it really hard as well. And what I mean on is that, oh, can you measure 45 degrees? Sure, but it won't happen at the minus 3 dB point, right? Minus 3 dB, or very close to it, and the minus 45 degree phase should be the same point, and you'll find that the phase is a little bit off. So the way you really would do it on measured data is find the 3 dB point, and then what do I notice? Oh, I go from 0 to minus 90. Oh, or near minus 90, because you might not be able to measure that higher frequency. But you can tell that if you're only going minus 91, you can tell that it's first order because there's a 90-degree phase difference. 2, you can tell it's not inverting because it goes from 0 to 90, right? If I was inverting that, the phase, we'll just say minus omega naught S plus omega naught, right? So how would I determine what the numerator would be, right? It would be 1 1 at minus 90, and then the numerator goes, like when omega is very small, right? The phase is 0, and then the phase goes to 90, which then when you take it into the numerator, it becomes minus 90. So you have minus 90 in the numerator, and it stays minus 90. At low frequencies, the denominator gives 0. At high frequencies, the denominator gives minus 90. Yeah. No. Oh my God. What am I thinking? It can be 180 or 1 at minus 180. Sorry about that. So I can try 180 and 0 and 180 and minus 90. That goes from 180 to 90. I can try minus 180. Convert that, minus 180. Minus 180 to minus 90 is minus 270. Well, these numbers are closer to 0 than this. So LT spice, the phase would go from 180 down to 90. Still, it's a minus 90-degree difference, right? And bless you. And so given that it doesn't go from 0 to minus 90, you know that it's inverting, right? So I don't really have to go through all of that. Is that the phase starts at 0 and goes to minus 90, that's standard not inverting. And then I see it goes from 180 to 90. Oh, that's got to be inverting, right? So then you would know whether to put a minus 1 or not in front of H of S. But once you find the 3D point or the phase point, you just read down, that's a kilohertz. Yeah, LT Spice does it in hertz, so you just convert it to radians. Okay. So the high pass, all right, the shape is going in the opposite direction, but we have S divided by S plus omega naught plus gain AC. So I come way out here, and what do I have? Oh, 0 dB. Well, again, gain AC is 1. Then I just need to find the cutoff frequency, which, yeah, you can do with 45 if you have a nice LT splice plot, and or the 3 dB point, and pull that off. Now again, this went from 90 to 0. So the S is always active. So the phase is always, and I'm just going to say low frequency, high frequency, right? And it's always 90, right? 1 over s plus omega naught will give 0 and minus 90, right? And a minus sign will give me 180 or minus 180, right? So I have 180. So 90 plus 180, $70 down to 180. 90 minus 180 is minus 90, 0. So now this case, it would go from 270 to 180 for being inverted, or minus 90 to minus 180 for being inverted. LT Spice would choose that one. Okay. But I guess the quick thing, right, is if you look at the phase and it starts at 0 or ends at 0, right? So the low pass is 0 minus 90. The high pass is 90 down to 0. I'll just put high pass, low pass, right? If you start or end at 0, it's non-inverting. So you're not having to plot it, you're just having to determine, is there a minus 1 in front of it or not, right? So that's non-inverting, and h of s won't have a minus, it won't be multiplied by minus 1.
For the 1s plus 39, right? It's minus 90, so it was s minus 39 would be 90 plus the icons.
So 90 plus 180, 270, 90 minus 180 is minus 90, right? Okay. Anyway, so remember that I said that it's really tricky to determine or measure the whole frequency spectrum, right? But you can tell from looking, here that the phase is starting at 90, and even if I can't measure it all the way out to 0, I know it's heading to 0, right? So it's not inverting, and if those numbers aren't that, now you know it's -1 times the transfer function or not. Okay. So, just going through some samples. Here we have a high pass. Here we have a low pass, right? Omega naught is 2 pi 10k kilohertz. Yeah, the gain here is 40. So the minus 3 dB point is 37, not minus 3, down here, but it's from the maximum value, right? And if I read over 45, and you can see it's very nice when you have LT Spice because it tells you what it is just by moving the cursor around. The gain is 100, right? But over here on the low pass, it's 20 minus 3 dB point is 17, right? Gain DC is 10, and yeah, bless you. And I did it, so that you still get the same cutoff frequency. Now, we're going to move into second order. But and you can see right there that second order is going to have minus 180 degrees of phase. So omega naught will occur at half of that, or 90. But it is extremely difficult to do this for a second order system. And so there's another way. That I want to show you. Now I do have a sample that shows you how to do LT spice in radians, but it's kind of a pill. So it's just better to I just want, you know what, I'll run it and then I'll let you know what I mean. So for AC, I want to do a decade, 20 points per decade is fine. Now, the frequency is 1 hertz. So I want to go, I want to center it around that. Okay. Now here's the thing. If I took the x-axis and blotted out hertz, right, and just called it radians, this would be the same thing if I put 1 radian. So 1 divided by s plus 1, and then change this axis to just radians, you'd get the same plot. All right. Now, yeah, if I click on this, it automatically comes up into the center. And so you have the 3dB and the phase right there. Now, again, I was about to tell you is that it's can be very difficult. So I want to show you the way you'll do it. So I want to, Oh, notes and annotation. Draw an arrow. So the easiest way is to do the asymptotic plot in reverse. Okay, a little bit hard to see because it's right on the axis, right? And then I come over here where the slope is definitely 20 dB per decade, right? So I just see that's too low, that's too high. I'm lining it up. Oop. I went a little too high, all right, but I'm not. Now this intercept, where you can't really see the upper arrow because it's right on the axis, but that intercept, so I just find that intercept. And of course, I know it's 1 hertz, so I'm drawing it right to 1 hertz, right? But you just draw down, okay? And this works for the other plots as well. So when you get a measured Bode plot, you can do this and find the cutoff for the omega naught, right? Much more easily than trying to, and much more reliably than finding the phase point. So really, I look at the phase, oh, it's going 0 to minus 90, it's not inverting. Then I do this asymptotic trick, and then I find the cutoff frequency is a hertz, and I look over here because I know it's low pass, and the gain is 0 dB or 1. Now, before we get into the other one, my notes show me doing the phase, all right? But I want to do a kind of a quasi. Okay, that's the magnitude, and we can just call that radians. So now what I do is I do asymptotic Bode plot. So there's the low frequency, there's the high frequency, just take it off with spray paint. Okay, so notice what I'm trying to show is there's a break here and there's a break here. This slope is minus 20, this slope is minus 40, but I just take the final slope draw a line and take this slope, which happens to be 0, and see the intersection. And what now I'm going to do is just draw a different Bode plot. Okay. You can see the two poles here, the two breakpoints. They're separate, so therefore it's underdamped. And there's no peaking. Here, there's some peaking because in fact it's underdamped. And that peak is not necessarily at omega naught. It can get very close. So really, again, the way to find it is you take this asymptotic, and then don't worry about the peak, right? You take this asymptote, okay, and then this intersection is omega naught squared. And then the phase you would find the same way, right? I mean, whether it's inverted or not, you would just find the same way. And then critically damped would be something like this, where it's 40 here, but you have this kind of roll off, okay? But where the asymptotic Bode plots intersect doesn't change for the same omega naught, all right? So that's just like the generic how to do it, intuitive way. Okay. So now let's go back. So I notice this is a low pass. So here's the low pass equation, right? You have omega naught squared, omega naught squared, omega naught, you have a damping ratio, right? You have a gain DC. So the gain DC is the same thing. I come to where it's very small in frequency and it stops, the Bode plot magnitude stops changing. I read off 40. Great. So that means the gain DC is 100. And see, I put 100 down here. Now, you need to do something at omega naught to be able to get the damping coefficient. Let's think about it. I have gain DC, that's something unknown. Oh, well, I can take it from this part of the plot, right? I also need omega naught, but I also need the damping coefficient. Well, yeah, instead of minus 45, take it at minus 90 because it's second order. But really, do it the extracted way with the asymptotes. So I get 100 hertz. Great. So now omega naught is 2 pi 100 hertz. Right? The damping factor is, now you kind of have to go through the derivation. We have h of s equal to j omega naught. So we're picking a point. So every time you see s, we put in j omega naught, and you got to work with the complex numbers, right? To where all of a sudden what you get is at j omega naught, you get the gain DC divided by 2 divided by the damping coefficient. All right, there's J, which then turns out to be minus 90, which is why you extract at minus 90, right? It kind of confirms it. So you read off, so now you're here, right? You read off the gain at that point, which I said was 14. Okay, so 10 to the 14th divided by 20 is 5. And then I calculate the damping coefficient and I get almost 10. And yeah, when I do these questions, I try to make things like really obvious, like a damping coefficient of 10 pushes these breakpoints really far away from each other. Because a damping coefficient of 1 or 1.5 or 2, it's like, well, 1, it's critically damped. It's happening at 1 point. It's really hard to tell, right? So, is it over, under, or critical? So I try to make things either critically way under damped, obviously, or over damped. All right. So that's and so that would be the process. So that's an underdamped, that's an overdamped system. All righty. Now we're going to do critically damped. All right. And I kept everything the same. But see, now you have this one breakpoint, but instead of happening at minus 3 dB, it's actually happening at minus 6. Again, all you got to do is draw a line from the flat line at 0 gain, and then draw this slope, and where they intersect is at omega naught. Great. So the gain is still 100. We're extracting at minus 90. Really, we're extracting the other way. And what is the gain at that point? It's 50. Ultimately, no, I'm sorry. It's 33-ish dB, 50, almost 50 linearly, and then you go through, and yeah, we get a damping coefficient of almost 1. Now it is 1, right? But reading it off, there's errors, right? So as long as you're getting close to 1 on an exam, that's good enough for me. But that's why I push it out like it's really underdamped, it's really overdamped, or it's critically damped. Okay? Try to make it obvious so that you can kind of check your work intuitively. And then here we go. Everything else is the same, but now we have the peaking. And if you look at it, it's really not on the peak. It's really to the right. It's just with my PowerPoint skills, it only gives you, it snaps to the grid, so you can't get exactly what you want. But again, just like I showed in the notes, I draw out a 0 slope line here, I draw out a 40 dB decade per decade line here, and it'll intersect, and then I can find everything. So the phases, the omega naught is still 100 hertz. What changes is now we're at almost 60 dB. We convert that to linear, and we get a damping coefficient of 0.5, which is really, underdamped. Now I want to point something out. As you know, I don't usually like confusion. A second order system has how many dBs per decade? 40. All right. So you can see that it's 40. All right. I have some DC gain. All right. Now I'm trying to draw the real Bode plot, not asymptotic. Okay. So So that distance is 3 dB. But it's second order, okay? This is in fact underdamped. Because if it was critically damped, it would be minus 6 dB, right? So then as you go underdamped, this rises. You saw when it was peaking, right? But this was second order underdamped, critically damped, and then as it gets higher and higher, right? Well, the damping coefficient under these conditions is 0.707, which is the Butterworth condition. All right. So sometimes you really got to look at what's going here. We're going to go over the time domain on Wednesday, but you really have to get this point here to ultimately get your damping coefficient. All right. And you don't have to see peaking for it to be underdamped. Okay. Well, now we just run through some other examples. Okay. I see 2 breakpoints. So over, under, critical.
I have a question on that last one. The drawing you just made. I guess I'm a little confused. How do you know that it's under them by just looking at it?
Because it's minus 3 dB down.
At -40.
It doesn't matter where it starts. This picture is a made up picture. I didn't tell you what that was. I just said it's minus 3 dB down. If it was minus 6, it would be critical, and if it was bigger than that, you'd see the breakpoints. Just follow the algorithm, really. So again, now I'm just reading it off of LT Spice. Again, I would just do the asymptotes for low frequency and high frequency. Where do they intersect? Come up with a mega naught. In this case, it's a hertz, right? Extract it at 90, so I know instead of another number, so I know it's non-inverting. But the gain at AC is 14 dB, right? And the gain at omega naught to do damping coefficient is minus 15. We better come up with a damping coefficient of bigger than 1 based on that plot. So at the frequency equals infinity, 14 dB leads to a linear gain of 5. What is the gain at j omega naught? Again, you work through the math, right? And you'll see that we're extracting at 90, right? So you have the gain at AC divided by 2 divided by the gain at j omega naught. And so we get around 15, which is even bigger than 10. So those breakpoints are very far apart. And so then you just substitute everything back in. So think about it. This was down by minus 15 and change. Now it's down about 6 dB. So I know that it's in the critically damped range, right? The gain at AC also happens to be 6 dB, right? the gain at j omega naught is very close to 0, right? So when you just plug everything in, right, the high frequency gain is about 2 at 34 millidBs, right? We get a damping ratio of about 1, right? And then you get the equation there. Okay. I'm thinking there should be an equal sign here. Okay. All right. Now, here's a slightly, this is less underdamped than the low pass underdamped, right? We come out, the gain is very close to 0. If you were to see, the slope would be 40, and the phase is going through a 180-degree change, so it's second order, right? But notice, it's right there in red, that omega naught is not at the peak, okay? And then you can just extract from there. So, because I see less peaking, I know it's, because I see peaking, oh, it definitely underdamped. Now, it doesn't have to have peaking, right, to be underdamped. It just has to be greater than minus 6 dB drop, or change, I should say.
It's pretty clean.
Because it's wrong. Because I copied the first slide and never bothered changing it until you came 5 years after these slides. Yeah, sorry about that. I got to go back and fix that. Now, this is where it gets a little bit trickier, okay? Before, you could find the DC or the AC gain very easily. You just look at high or low frequency. Then you could find omega naught with the asymptotic approach fairly easily. And then you could use a very simple equation to find the damping coefficient, all right? But that's because everything was kind of happening at different points on the curve. Just like if you have two unknowns, you need two equations, right? Well, we have omega naught, the gain, and the damping coefficient. So you have three things, right? So you should kind of need 3 points. What it is the damping coefficient just has the high speed, the higher the low frequency gain divided by the gain at omega naught. But when we do notch filters and bandpass filters, it doesn't work that way. So you can, at omega naught, there's not enough information. So you actually have to do it a different way, all right? And so here's the band shape, right? You're selecting a frequency, right? I'm not showing you the phase per se because the thing is in front of it. But yeah, it'll go from 90 to minus 90 for non-inverting. All right. You can see how I programmed LT Spice to give me what I want. So if I take asymptotes on this way and that way, I will intercept at the peak. So in fact, the peak is omega naught. That's easy to find. But then that gain here at midband is this gain. And so now you've used up that data point, and so you can't calculate the damping coefficient. All right. So what you do is you go plus or minus 45-degree phase around it. All right. And they just call it FC. And you subtract, so you find where you're at minus 40, or this should be plus 45. You find it where it's at minus 45-degree phase, you get that frequency, right? Subtract them, and they call that FC. But it's not cutoff, it's just FC. And then that gives you the damping coefficient. So you have omega C divided by 2 omega naught, and then you get 0.713, which would have been the Butterworth condition, right? Because the damping coefficient is 0.707. So I don't want to beat a dead horse, but here, right, high frequency gain, you find omega naught from the intercept, and then this point at omega naught also gives you the damping coefficient. But notice how we find high frequency gain here, we find the gain at omega naught here for damping coefficient, and then we get omega naught. But the problem is at the midband, we've already, notice how we have damping coefficient and midband happening at the same point. That's why we do this plus 45 and minus 45. Which took me a long time to find out. Excuse me. I had a much harder way to do it. And, but you can see on the bandpass, right, now when the damping coefficients get smaller, it gets narrower, right? It's more selective, right? In fact, right, if the damping coefficient went to 0, right, you'd have omega naught square. Let me come back. Here's the bandpass, right? If the damping coefficient was 0, this would fall out. I'd have S squared plus omega naught squared, right? Which is like an oscillator, right? It's out of control system. Okay. Anyway, now I find omega naught because it's at the peak. I find the midband gain, great. And then I just go my minus 45 and 45, find the difference. And voila, I get a damping coefficient of 0.1. Now I have a very large damping coefficient, and the band that's passing is quite large. You can see that it still goes from, well, actually the phase isn't going from the phase as shown isn't going from 90 to minus 90 because I just didn't plot it out that far, right? Notice you can really see F1 and F2, right? Where now I get 20 kilohertz and I get 10.1, all right? So you can see as damping coefficient gets bigger, the two cutoff frequencies get farther apart. The notch. Okay, so damping coefficient of 1, and yeah, I have the two gains the same. You can have them different, but so in this case, right, you notice that the attenuation goes down or it's more attenuated at the cutoff frequency. The phase does this kind of, it goes down and then goes up and comes down. So it's a very notch-like thing to do. All right. But really, you just pull off the same process. You pull off the 45, the minus and plus 45, come up with a frequency difference, convert it to radians. Although, yeah, it would just, the two pi's would just cancel out, right? And you get one. So the damping coefficient is 0.65, not 1, and the gains are 0. The gains are 1 and 1. So that's another type. Okay. But really, you find the frequency difference centered around omega naught, and you can see the gain hasn't changed from 0 dB or 1. There's no more. It's not a lot of notes. There's some plots I did, but I might have done it. Oh, here's a pro tip. Don't try to write things in there in the data source. So V equals V1, the plot, plus equals squared divided by S squared plus 2 times omega naught makes it a variable. I'll just call it Z for damping coefficient. S plus, oh wait. I could have programmed that too. Omega naught squared, S squared. 2 times omega naught times the damping coefficient. It's that. So much easier than trying to write things in there. Okay. Spice directed. Step. Decade. Step, decade, Z. 0.1, 10, 5. So step that variable from 0.1 to 10 in terms of decades, 5 steps per decade. gram omega naught equals. Actually, it's not, I don't want it to be omega naught. I really want it 2 times pi. So it's really, yeah. Okay. Step. You know what? Let me just say dot param z equals. Do it the inline way. All right. So there's with the peak. No, I really. Oh, that's right. Dot deck. No. Step deck. That's it. Thanks, Joe. Does deck come first? Start value. Start value 1, 10. Step deck. Isn't that what I had? Oh, that, or maybe I forgot Z. All right. So now I think this answers your question maybe more, George. Is see how the omega naught never changes, it all crosses, right? And the phase either sharply transitions or slowly transitions. But omega naught, the gain at omega naught, right, keeps going up as the damping coefficient goes up. And so let's just try to zoom in so we can see the 3D. Okay. So here, we can see that the gain at 1 hertz for these for these higher damp systems is much lower, right? Like these 3 lines, you can't even plot in at the, I don't know, tan line, right? The gain is like minus 17. Then at the blue line, it's like minus 10. Then at the green line, minus 6. So that might be very close to critically damped. Then here it's, I'm just eyeballing it, almost minus 3, right? Then purple, well, you can see it peaked a little bit, but it's very close to 0. And then it keeps getting higher and higher and higher. And so the higher it is, right, the more underdamped it is. Right. Then you want to see it for high pass. Just change the denominator, numerator. Right? You see the same functionality. Okay. Now, yeah, notch. In a way, it's easier because I just have to put a parentheses plus right? High plus low. And then notch. Two times stamping times. Wait, what did I use for Megan? Sorry. Ah, I forgot the S. Because that's a low pass. The gain is lower because it's not omega naught squared, it's just some constant. But now we have bandpass. Okay. I had these other notes. I'll have to find it. I did some measurements. Just can't believe I would have deleted it. Oh, here it is. So these are actually measured from the oscilloscope. I had some Python code generate it. You can see the phases jumping around, and you just see that I go and extract it. And this is more of a maybe next time. But that's just what I wanted to show you. Is that's what it would look like. And see, it doesn't even go down to 180 because the frequency is too high. But I know that it's not inverting, well, because it was an RLC filter. That's pretty much it for today. Just a comment. I don't see a lot of notebooks. Okay. Did I say I don't see your notebook? No. I said I don't see a lot, and I'm trying to gaze around. Okay. So listen, yeah, I know I'm making the video, right? So it's there, but the video's not going to help you on the exam, right? Writing things down makes a mind-body connection. Okay. So even if, and to be fair, listening to an hour and 15-minute lecture to find your information, even on high speed, is difficult. All right. It also indicates a passivity in your learning. Indicates, I didn't say was. And just so you know, if you want to be active in your learning, go to room 376 right after class. It's led by Joe and Naomi. I know they're there. So that's where the study group is. They're very welcoming people. Yep, I put you in charge of it, so.